Okay, let's go over how you recompile the kernel. There's a command called makeOS okay, on my system it's D is the drive. Now if you're compiling to for a CD-ROM, if you want to make a kernel for a CD-ROM, you have a different destination. This is anyway. You can look at this code. It's got so what it does is it calls a make, and then it writes to the boot sector. Here's what make all does. I've been talking about this kernel and compiler. Compiles those, makes those into binary files, static binaries, and then it writes to the boot sector. It writes the block address of the kernel, and it stores it contiguously. Anyway, so we're going to go ahead and do it. Now, when you compile, it hits some compile time executable code. It's asking for the account drive. Okay, well, I wish I didn't have to ask so many questions. We're going to say D. On your system, it'll be C and C for both of those. Now, it doesn't know how to mount. You have a fixed entry for what's mounted. And that's stored in the kernel. So this is the first drive, the first letter of, let's say you have 3 partitions, it might be C, D, E. On my system, it's D and E. Anyway, RAM drive, hard disk, or CD-ROM. We want hard disk. Probe. Now, it's a little known fact that you can have port I/O access besides primary and secondary. There's a good chance your system will be ACHI, which is not going to work. You have to run in VMware, but it will work if on some systems. If from about 2003 to 2010, you probably have a system that had some other drive, some other port for the drive. Anyway, so it might not be able to even list it. You can either enter port numbers, or if it finds it, you can enter it's kind of a kludge. If it's a tiny number, it knows it's 1 or 2. If it's a port number, it's bigger. Anyway, so we could do a RAM drive. We don't want a RAM drive. Normally, well, anyway, startup account. For my system, it's a 2-level directory. Yours is probably just a 1-level. This is a directory in the account directory, accounts directory. Now we're done. Now, if you want to do strange stuff like text mode or no multi-core, if you want to initialize memory to a non-zero value or something, actually it doesn't initialize to 0. It doesn't initialize, period. Anyway, we don't want any options. So there, we just compiled the kernel. So I can reboot now with RAM boot or hard. Anyway, now you might want to install a master boot. Master boot install. We just installed on the first block of the partition. We just put the we just put that on the first block of the partition. So if you have grub, it works. But maybe you want to replace grub, then you do a master boot install drive letter drive list. Now it stores on one partition, and if you want to do D&E, you do this. Actually, it will I'm going to go ahead and do it. Okay, so it found D and E and it made a master boot. So let's go ahead and look at what's happening. Here's the CD-Rom boot. You can understand that if you can understand the hard disk. This goes on the first block of the partition. So what it does is it copies itself up to 96C0. The standard is it loads at C7C00. Anyway, it copies itself out of the way. Then it loads one block at a time of the kernel.bin. When we install the boot sector, it writes the block address into this location. So this is ready and waiting to go. This is the this uses interrupt 13, which some people will try and fool you with the old-fashioned number 2, I think. The only one you should use is 42 because hard drives are big. Anyway, so after it loads it down at 7C00 after it moves itself out of the way, and I don't have complete 16-bit assembly. I didn't do segments when I made my assembler because normally you're in 64-bit mode, so I had to hand code the 16-bit. This is a jump to 7C00. Now you can follow the link. This is where it goes to. When it loads. So here's the install code, by the way. It's in the Atom boot directory. Now that was the Atom boot directory. Now we're going to the kernel directory, and it starts with when you compile the kernel, it just puts it's just a bunch. This is like doing an A.out. There's no object files, no linker. It just does a flat binary. K-start is the first, and this is some 16-bit code. When it starts up, it does a couple BIOS calls. It changes to graphics mode, VGA 640 by 480. That's what it does right there. It gets the memory maps from the BIOS, and it changes the address line. That's legacy crap. Then it sets up the GDT. Technically, this is relocatable. You can put this module anywhere, and it will set sets the GDT. I don't have a 16-bit compiler. I just made a 64-bit. It would be way harder to do a 16-bit compiler. I had 16 registers to work with, and anyway, but we're trying to get to 64-bit mode. So here we're jumping into 16 to 32-bit mode. We're starting up 32-bit. Now my flat binaries are position independent, but they have a patch table, so it self-patches all the absolute addresses in the module. So it's going through a list that's stored in the binary file. The binary is executable code, and it's also a symbol table, and it's also a patch table, and it self-patches. So don't run anything before here. Anyway, so now it's been patched. Then it jumps over to the memory file, and it initializes memory. It identity maps 128 gig. Then it jumps down to change to 64-bit mode. That's down here. If you want to know how to change 64-bit mode, turns on virtual memory right there, paging. It has been identity mapped, and jumps to a 64-bit code segment, returns back up to where we were. Then it sets up this is the Atom task is what it's called. So what are we doing? We're setting up the CPU record for the core 0. We're setting up the heaps and block pools. I think we're setting up the, what are we setting up? Setting up the heap for the Adam task. This is Adam's heap. He has a code heap and a data heap. Sets up his queue links. So right now, I have a run level which keeps track of what has been accomplished. We just set the boot heap. If you want to see what the different steps are, it starts in 16-bit mode, it initializes VGA, initializes 32-bit mode, patches the absolute addresses, switches to 64-bit mode, sets up the boot heap, sets up the full heap, sets up the raw screen I/O. Before this point, you can't write to the screen. Sets up the interrupts, sets up multiprocessing, sets up the disk, sets up the compiler, sets up the window manager with these documents for command lines. You need the document framework. Sets up the window manager, logs into the account, does the account files, has done the registry. During the registry, the account registry has some stuff. Oh no, it doesn't execute the registry there. It does all the account. There's no account code has been done. Adam stage 1 is the kernel. Stage 2 is it goes into the Adam directory and does that Adam 2 file. Then it sets up the then it goes into a standby mode of serving clients. So that when the Adam task has gotten to, when it's finished startup, it's in standby serving clients. Anyway, so where were we? So now this is the start, kernel start. Then it jumps to kernel main, which is where this is kind of like, now it's in C. Before it was assembly. So we're in 64-bit mode. It's identity mapped. Now we do the initialization so initializes the heap, initializes the global variables. Global variables are 0 because they're just gaps in the binary file. The kernel binary file is just a flat binary. I don't support ELF. My compiler does not support ELF. I don't know if this is the kernel. No, I don't think so. I think we go the kernel binary. I get confused a little bit. This is the kernel binary that's used. It's in the root directory. So the kernel binary is flat. It's contiguous. The global variables are just gaps that are initialized to 0 if not otherwise specified. So we initialize globals. We initialize 32-bit devices. That doesn't really do anything. We mark. I do null dereference crashes. Some guy was bragging about making null $1 billion bug because null dereference was not caught. So I went ahead and if you reference null, it crashes. Load the kernel. That loads the symbols into the symbol table. Initialize the black and white raw I/O. Isn't that what? Yeah, I think that's what that is. No, it's not. It's not the raw I/O. Initialize. I know. Okay. Anyway, load some defines. Bootstrap processor is the core 0 processor. At this point, it's initialize raw I/O. Initializes the timer, initializes interrupts, calibrates the timestamp, counter, timestamp frequency, initializes the mouse. I think that's done in parallel. Yeah, it's done in parallel. And loads the compiler. So we have to be able to compile the command line. Then it loads the kernel, and when we're all done, we execute Adam 1. Adam 1 is like auto exec. Then when we come back from that, we go into standby. We never return, entering a server loop. So Atom 1 is what we do next. We load the symbols, the header files for kernel.bin and compiler.bin. We load the header files, and then we jump over to Atom 2 and do the rest. And in the Atom 2, we include about 40,000 lines of code. Then we jump over to the home directory and do Atom 3. Your home directory is in the accounts directory, and there's Atom 3. So it does localizations, packages, keyboard plugins, wrappers, and then sys. Let's go ahead and look at the sys. So Atom 3. So if you want a DLL, just add a package into your account packages directory. Atom sys is when it gets ready to start up, it spawns a couple tasks. That's why you start up with 2 tasks, two terminals. Anyway, so a terminal, if you want to know what a terminal is, it's a task that it spawns a task, and it gives it the user command line as the startup, and the user command line executes some stuff, and it continue user task. The lexical analyzer for the compiler is invoked, and every time it needs text to compile, it fetches from the keyboard buffer. So the compiler literally, the compiler is running, and it pauses for you to enter text. That's how it operates. Pauses for you to enter text, and then if it's when you enter text, commands outside functions execute immediately, and functions get stored into memory. So guess how you run a file? We're going to go to the demo directory. Let's look at the exceptions. This is just a demo. Guess how we run it? We say, remember, the command line is feeding into a C compiler. Exceptions.cpp.c. Now some people think these are archives. No, it's individual files are compressed. I think we happen to need a semicolon. So this is this little demo. Shows how exceptions work. By the way, exceptions, you throw a character string of up to 8 characters, and then when you catch it, you access off the task register the last exception if you want. Otherwise, you can just catch it. Anyway, so it's brutally efficient. Anyway, so that's how that works. Startup.